Hi folks, this is Calc 2 Checkpoint Quiz 3. We're given a function, f of x equals tangent x minus x plus 1, and we're restricting our attention to x's that lie between minus pi over 2 and pi over 2. And in part A we're asked to prove that it's 1 to 1. And in part B we're asked to find the slope of the tangent line to the graph of its inverse at the point pi over 4, negative pi over 4. So how do I prove f is 1 to 1? Well, we can use calculus and try to show that f is either always increasing or always decreasing on that interval. So I take the derivative here. The derivative of tangent of x is secant of x squared minus 1, and then the derivative of 1 is 0, so I get this guy. How do I show this is always increasing? Well, I go back to Calc 1 and I make a sign diagram for the function f prime of x. First thing we look for, are there any places where f prime is undefined? Well, in order for f prime to be undefined, the only thing that could be troublesome would be the secant of x being undefined. And that would be any place where the cosine of x equals 0. So I look on the interval I'm considering here, and cosine x is never 0 on this interval, so that means f is always defined. So there's no places where it's undefined. The next thing I look for then is I look for where f prime of x equals 0. And so I set the derivative equal to the 0, and I get secant of x is plus or minus 1. Secant of x is plus or minus 1. That's the same where cosine x is plus or minus 1. And the only time that happens on the interval negative pi over 2 to pi over 2 is x equals 0, in which case the cosine is 1. So now I go off and make a sign diagram for the derivative f prime of x. And because of my restriction on the x, I don't need to worry about anything to the left of minus pi over 2 or anything to the right of x equals pi over 2. The only critical value I have in the interval is at 0, and at 0 the derivative is 0. Now I check around this, say negative pi over 4, pi over 4. You plug either of these into the derivative function, you're going to get their secant squared is 2, so 2 minus 1 is 1, so that means the derivative is positive on either side. So what do we have? We have the derivative's positive here, that means the function's increasing over here. At 0 it flattens out, so we have a horizontal tangent, and then it's increasing again on this interval. And we know from Calc 1, as long as we have increasing intervals, we could have a few points for the function where it's a horizontal tangent, but if it's just finitely many, then the function's always increasing. Okay, so we know that from the sign diagram, f is always increasing. Oops, always increasing. Which means f is 1 to 1. Okay, so I'll do it for part A. Alright then, so now that we know that f is 1 to 1, we know f has an inverse, and we're going to call that g. And we want to figure out the slope of the tangent line to y equals g of x at the point pi over 4 comma negative pi over 4. So we want to use the result from class that the derivative of the inverse at a point B is 1 over the derivative of f at the corresponding point A. And so here the idea is A comma B is on the graph y equals f of x. In other words, f of A equals B. And this is the same thing as saying B comma A is on the graph y equals g of x. In other words, g of b equals a. All right, so in this case, we're given the point on g of x is pi over 4 comma negative pi over 4. So this is acting as the b, this is acting as the a. So that means that g prime of pi over 4 is 1 over f prime of negative pi over 4. Alright, so what's f prime of x? We had from the first part, secant of x squared minus 1. So f prime of negative pi over 4. This was actually one of the test points we used in part A. The secant of negative pi over 4 is square root 2. Square that minus 1, you get 1. So g prime of pi over 4 is 1 over 1, which is 1. So that'll do it for part B, and that'll do it for number 1. Okay, number 2, we're given the function f of x equals natural log x, and we're asked to prove f is 1 to 1. Now remember from class, by definition, the domain of natural log is x bigger than 0. And so we go ahead and do as we did in the previous problem, we take the derivative. And by definition, the derivative of the natural log of x is 1 over x. All right. Well, we could make a sign diagram. We could go through the formality of this. We know that we don't need to worry about anything less than or equal to 0. But whatever we pick over here, say x equals 1, it's going to be positive. Okay? So since f prime of x is always bigger than 0, f is always increasing, hence 1 to 1. Now I move on to part B. Let g equal f inverse of x show this remarkable property. G prime of x equals g of x. Alright, so how do we figure that out? Well, we know from class g prime of b is 1 over f prime of a, provided f prime of a isn't 0, where a equals f of b, f of a equals b, which is equivalent to g of b equals a. So if I just want a generic expression with x, g prime of x, that's going to be 1 over f prime of what? So x comma what is on the graph of y equals g of x? Well, g of x. Okay, so here x is acting as our b. Alright, so b is x, which means g of b is g of x. And that's all the more we have for it. Alright, so let's work that through. So g of x, or g prime of x, is 1 over f prime of g of x. Well, what's f prime of x? It's 1 over x. So what's f prime of g of x? That's 1 over g of x. So g prime of x is 1 over f prime of g of x. That's 1 over g of x. And we go through the fraction gymnastics, 1 over g of x. That's just g of x, which is exactly what we were asked to show. Alright, so whatever this inverse function is, it's its own derivative. And that's what we'll talk about in section 5.4. That'll do it for number 2.